So the 2013 WT and Idali Reed Prize goes to Tyrone Duncan. The WT and Idali Reed Prize in Mathematics was established by SIAM in 1993 to recognize outstanding work in or other contributions to the broadly defined areas of differential equations and control theory. Tyrone Duncan is a professor at the University of Kansas, and he has been active in SIAM as a member of several committees, editorial boards, and conference organizing committees. Mm-hmm. Yes. He is an IEEE Fellow and an IFAC Fellow. Yep. The 2013 WT and Idali Reed Prize awarded to Tyrone Duncan for his fundamental contributions to nonlinear filtering, stochastic control, and relation between probability and geometry. And the title of his lecture is Solvability for Stochastic Control Problems.
Thank you, Irene, and thank you to the audience. I know I'm competing with San Diego weather, so I appreciate that you decided to come here and not take advantage of the weather. Also, I'd like to extend my strong thanks to the Reed Selection Committee, George Yin, Alain Ben-Susan, Suzanne Lenhart, Michael Weinstein, Ricardo Rocheto, and also for the Reed family for providing this award, and well, especially to the person that we're, primarily focus on is William Reed and the Riccati equation. And you'll see in this talk that we'll actually see Riccati equations appearing again and again because they're obviously very intimately related with optimization problems. And we could spend 30 minutes or more talking about all that relationship, but we won't. I have to be aware of my time and all that too. So we'll get started here. So what we'll look at is some methods for solving the stochastic control problems. Linear quadratic stochastic control, but not in the conventional sense. A linear exponential quadratic Gaussian control, control of Brownian motion in a sphere in a real hyperbolic space, and some generalizations of these things. So the major methods for solving stochastic optimal control problems, I would say, the following two things. The Hamilton-Jacobi-Bellman equations and the stochastic maximum or minimum principle, whichever way you set up the thing. So what we have there for the Hamilton-Jacobi or Hamilton-Jacobi-Bellman equation, two things. We have, well, in the deterministic case, we have this first-order nonlinear partial differential equation. And in this second case, for a stochastic problem, a problem, say, of diffusion type, we get this additional operator here from the generator for the Brownian motion. And we have to solve this thing. So we have a second-order nonlinear partial differential equation. Here we have a first-order equation. And we'll look at, and in the, one kind of comment, just briefly, this maximum principle, what you solve, you get a necessary condition with some convexity conditions, it becomes sufficient, and you have to solve a backward stochastic differential equation, which means that you solve backward in time, but you have a forward in time measurability. So now we'll look at this very well-known problem, and if anyone has studied anything about control in continuous time, one has seen this problem. So, if I don't touch the right things. So we have here deterministic problem, here the quadratic cost functional, and here we have this close relative, the stochastic problem. And first of all, we'll just think about this as a standard Brownian motion. So we have these two problems. And now what's kind of curious about these things, well, let's look at what we have to solve. So we have to solve, in this case, deterministic case, this Hamilton-Jacobi equation, so we just put in what this Hamiltonian is. So we have the cost functional and then this adjoint variable or kind of a generalization of Lagrange multiplier indicates directions we can move from the differential equation. And then we have likewise this second order one here. Now, what's interesting about these things, at least, or unusual, is that in both cases one gets the same solution. And of course, you have this, and the P here is from this Riccati equation. And they say the solution is really this quadratic form in the deterministic case, and in the stochastic case, you get just an additional function of time. And now, it always bothered me, why should the solutions be the same? Well, kind of standard answer is, they're both the quadratic form. Well, at one level, that can be satisfying, but I don't think it's very satisfying because it doesn't address, intrinsically what's going on. Why should they be the same? Why are they the same? In other words, is this just, by chance in this problem, or is there something more going on here? So that's something we want to look at. And let me go back here. So what we're going to do now, in this problem here, if we, wherever we are here, there it is. So now, instead of taking this Brownian motion, so we'll look at this more naively. Now, actually, I grew up in stochastic analysis, so, one would say that's the Brownian motion or something. You can't just treat it as just, an arbitrary affine term that you add to the equation. But if one is, say, somewhat more naive and says, well, this is just some additional affine term in comparison to what we have up here. And actually, what's remarkable is that you can actually do things just thinking about that in a relatively naive sense. And that's what you started to indicate here. So what we have here is actually that solution. So W is just a process with square integrable, and it has continuous sample paths. So now what we have, the optimal control, we have this piece here, which is again what we saw for the deterministic case and the case for Brownian motion. And we have an additional term V here. And basically what we'll see, actually that's taking care of this additional affine term we had in the equation. And again, we have the same Riccati equation, and the V is determined in the following sense here. So what V is, so what we do, we take the dual or adjoint of the optimal system and look at the response of that to this future noise or disturbance or affine term, whatever you like to call it. So we do that, and then what we do, we get the conditional expectation. So this is the estimate or prediction of the influence on the optimal system to this future noise. And that's and that's how we get out the solution from that thing like that. So, and in special cases, well, we can be a little bit more concrete, because if one knows about conditional expectation, it's like kind of swept under the rug. Normally how one defines conditional expectation, it's actually you appeal to some kind of Radon-Nikodym kind of thing. You get some measurability with respect to some sub-sigma algebra, and that object then is a conditional expectation. But we can actually write it concretely if you, we'll see what these things are actually. So if this thing is a standard fractional Brownian motion, and so I'm a little bit out of order because I haven't defined what that is, but we'll get to that in a moment. So we have this thing that conditional expectation is actually expressed in this form here. And we know from Gaussian things that actually it has to be a linear functional of what we're conditioning on. And so we have this then Wiener type integral for this process. But the only thing is you write it explicitly. Here's the integrand. And these things are, depending upon what you see in this exponent here, these are either fractional integrals or fractional derivatives, like that. And And we'll see what they are concretely in a moment. But now we're kind of going backwards, as they say. Now we'll define what those processes are. So for each h in 0, 1, h is called a Hurst parameter. We define a Gaussian process. And it has continuous sample paths, or there's a version which has continuous sample paths. It has zero mean, and this is the covariance. So in fact, for example, if you take h equal to 1/2, you get Brownian motion. But then you get a lot of other interesting things. And you can call this other thing, this formal derivative, fractional Gaussian noise, just like we call white Gaussian noise for the case of Brownian motion. So, and here are a couple of properties of things. If you scale in time, then these two things are equivalent in law, like that. This is an important property. It has a long-range dependence when h is between 1/2 and 1. And that just means here, concretely, is that this is the first increment of the process, because you start at 0, and the n plus first increment. So what that means is that covariance goes to 0 relatively slowly. And that has implications on the behavior of the process then, and actually what's useful for applications. And here's something else. All these things have unbounded variation, and actually you have a pth variation. When p times h is equal to 1, you get something which is non-zero and finite, like that. And give you an idea of things. Here are some applications of things. Actually, it was Kolmogorov who defined the processes in 1940, and he was interested in this first thing, turbulence. Harold Hurst was actually interested in hydrology, and he didn't really define the process, but he did the first really statistics of it, identifying this thing we call the Hurst parameter, which actually classifies these processes. And actually, he was interested in rainfall along the Nile River basin, and what he's interested in is having a reservoir there, which actually, eventually they did get a reservoir. And actually, so what you want, two conditions for the reservoir. You don't want it to overflow, or you don't want it to run dry. And so you're interested in this behavior of the rainfall. And since the rainfall was such an important thing to that area, they had extensive information about it. And you can see information about these things, going way back, where it rained for 40 days or 40 nights, or there were 7 years of plenty, 7 years of famine. So it's very important. So what he did, he took 850 years of that data, and he saw that the rainfall was not independent from year to year. And he identified this H. It was approximately 0.75. What he got. And then there was Mandelbrot, who was interested in economic data, used these processes, and actually coined the name for the thing. And then subsequently, they were in telecommunications, saw the usefulness of this in the 90s. Earthquakes, since we're in California, it's appropriate to talk about earthquakes, or perhaps not to talk about them. But again, this is a model for behavior. The occurrence of earthquakes seems to behave as they identify a Hurst parameter, again, which is something greater than 1/2, like that. Epileptic seizures. So the time between seizures, people have identified based on data, again, a model for this from the fractional Brownian motions, cognition, biology. But the point is that, in other words, that using Brownian motion, one has traditionally done this essentially by the usefulness or ease of handling things, but not based on kind of the reality of the process itself. And so we have these kind of things. And, as I mentioned, the major contributors were Hurst and then Mandelbrot. Mandelbrot did many things, did things with fractals, things like that. And perhaps I'll give you a little brief aside about this, about Mandelbrot. He studied actually in France. He had a choice of going between, after World War II, He took exams both for l'École Normale Supérieure and l'École Polytechnique. He was admitted to both of those, but he preferred l'École Polytechnique because he had really interested in something applied. And I got a master's in Caltech. He came to the U.S., went back to France to get his PhD, but eventually he came to the U.S. and he went to work for IBM Research in Yorktown Heights. He worked there for almost 30 years. And the only reason he left is because IBM changed policy about research. They weren't interested in that kind of research. And he went to Yale at age 63. And he was at Yale for 12 years before he got tenure. So at age 75, he got tenure. So you young people, don't worry. Don't feel pressured about these things. You have a whole lot of time, you see. Just remember Mandelbrot. I think it's kind of an extreme case, at least that I know of, getting tenure at age 75. And after waiting for 12 years for it, Okay, so, and here's something else about these fractional Brownian motion. One knows for a Gaussian process, there's always a natural Hilbert space associated with that. Well, this is the one here, and here are the definitions of fractional integral and fractional derivative. But we should keep moving here. So here's another problem. It's called the linear exponential quadratic Gaussian problem. And so we essentially have the same system we had before. Now we just use Brownian motion here. I just put in this linear transformation f in there. The same kind of conditions here. The interesting, what the deviation from before is that now we have an exponential quadratic cost. We put in this parameter mu. At least when mu is positive, you look at it this way. When mu is negative, you stick out another mu here. You do that. Anyway, so these things are sometimes called risk-sensitive problems. And this kind of thing, when mu is positive, that's someone who is risk-averse. And what one sees mathematically, and also actually even physically, if someone is too risk-averse, what do you tell them to do? In other words, they don't know what to do with their money. And the same thing with the mathematics, it just breaks down. Tell them to put it in their mattress or something, but, there's nothing that they can really do there. But what we're interested in this thing is the following. It is something proved by Jacobson about 40 years ago, that actually, again, we have this linear feedback control. We have a Riccati equation, but now it's a little bit different. So we have this term here appearing like that. Now, why does that term appear? I think, again, a legitimate question. Well, one can say, well, if you take the Hamilton-Jacobi-Bellman equation and solve it, then this works. So that's justification. Well, I don't think that explains things too well. And actually, we see the rest of this. You have to see the costs and things like that down here. But actually, I'll just give you a sketch of the proof. Using some other way, and you can see why that term appears. So what we have here, so if you take this term here and make it a function of t, take the differential of that, and then integrate that differential using the Riccati equation, you get this expression that we have here. These things, you collect terms, you get something which is a square, and then some other things here. Now, you see, if we had the linear quadratic problem, without doing the exponential, you just take expectation here, and this term here, stochastic integral, would disappear, because that's zero mean. However, you see with the exponential, it doesn't disappear like that. And so what we do to take care of it, we put in this term here, which is that other term you saw in the Riccati equation. And this thing here is the increasing process associated with this term, this martingale. In other words, you let capital T vary. This is the martingale. This is the increasing process. Once you exponentiate those things, you get an exponential martingale or a Rado-Nikodym derivative. So what you do with that term is actually you change the measure. So that's how you take care of, this stochastic integral term. And that's why you need this term, because you have to get the Rado-Nikodym derivative. So that's why you would do that thing there. And And associated with those things, you also have the notion of stochastic differential games. So you have two players, U and V, in this setting. And you have, so one player wants to minimize, one player wants to maximize here in this setup. But and you have some conditions on admissibility, and there's general kinds of things for the U and V that we have here. But let me just get down to this thing. So here are the optimal optimal strategies. And now we're assuming that the noise, again, is some more general kind of process. So that's how we get this other term appearing here. But anyway, what you see here is that, see, this term here looks analogous to what we had in the exponential quadratic cost. If you that mu f transpose term like that. And so you have this kind of term here. And that other term, as I mentioned, was just what we get again from the optimal system. Now we have from the two players. And then we solve that backwards and we do the conditional expectation of things like that. So that's what we would do that. Okay, so we want to move on to some other things. So here's one which I'll only briefly state. In other words, what about stochastic partial differential equations? Well, here's one kind of setup, that we can do. So we have this thing just kind of written formally, this thing in an infinite dimensional Hilbert space. A is an infinitesimal generator of an analytic semigroup. B here, so what we're allowing here, the control to be on the boundary or just at discrete points. So B has this unboundedness property indicated by this fractional power of the domain. And C is Hilbert-Schmidt, so what it takes this thing here and regularizes this noise here. And you have a quadratic cost, analogous to what we had before. And you have a Riccati equation again, but you have to interpret it in a little weaker sense. In this form here, this weak sense, you take x, y in the domain of the generator, or you look in this mild sense like that. But basically, on one hand, it is again a Riccati equation, which does the solution for things. And then now you get the same sort of thing. We get these two pieces here, and the second piece here is again this conditional expectation. But now notice we're only doing this, I didn't mention that, only here is for h between 1/2 and 1, because things are a little trickier, in this infinite dimensional setting like that. So now I'd like to see, and basically one major component of these problems is actually solving it by using a completion of squares, as we saw. That's one piece of the thing. But I want to show that actually this is not restricted to the equation being linear. So here we go with some other things here. So we'll look at Brownian motion in H2, a real hyperbolic 2 space. And what that is a symmetric space like this. So the subscript 0 means the component identity. So this 2-1 means you preserve that form with 2 plus 1s and 1 negative 1. That form. It's the matrices would do that, and you take the quotient like this. And we just put in this one here to see what happens when you can put in P and Q, as we'll see here. Anyway, but probably a more comfortable thing looking at it is you can view this as the open unit disk in a tangent space with this metric. So it gives a Riemannian metric, so the boundary looks like infinity, like that. And that's what we do. And so what we're interested in is control where we're worried about how far we are from the origin, nothing in relative position of things. And so what you have here is this stochastic differential equation, like this. And we'll take this as the cost functional. Now I'll show you in a moment why we make choices like this. But the point is that we can take this thing and we can actually solve this thing explicitly. And we have that here. So here's the solution. You have the hyperbolic tangent here, like this. And we get a Riccati equation in the solution, like that. So, and here's the optimal cost, what you do there. And you can do this thing more generally. So you can take any one of the rank 1 non-compact symmetric spaces. So here are the real ones. So that's why I brought along 1 and 2 and 1 before. You do P and Q. We can do the complexes or over the quaternions. We can do all those things. And how you get the cost functional is the following way. So what we're looking at here is what's called a radial part of the Laplacian. And that differential operator, the radial part of that Laplacian, looks like this in general. So we have this second derivative term, and we have these first order terms like that. And you solve that thing by doing a change of variables like this. So you get a second order linear equation with variable coefficients, which one they actually solved, even in a first course in differential equations. So you can use power series. And the power series we get here is from the hypergeometric functions. And you take m as a positive integer, you take negative of that, those you get polynomial solutions, and you make the substitution like this is the eigenfunction. And that's why we got the hyperbolic sine squared. And then you can see how you do that. So you get a whole family of solution of examples doing like this. Now, we can also change to its close relative, the two-sphere. So this thing is a rank 1, again, symmetric. It's compact now, rank 1 symmetric space. It's SO3 mod SO2. So it's simply connected, compact thing. And you can think of the metric by restricting the standard metric in R3. So you do this in calculus, this kind of thing here. So you have this map. So it's a diffeomorphism as long as you don't go to the antipodal point here, which has length L, capital L, pi in this metric here. And the Laplacian in that form is these two terms plus the other term, like that. These two terms are the radial part, again, of the Laplacian. And so again, we can set up a control problem. So where we put in the control now for that thing, we want to get to stay by the origin. So here we have this thing. And the radial, so if u is a smooth function, you have this as a generator, like that. But in general, you don't want to just initially restrict that the u be, have some smoothness in x. So we have this thing. And this is the cost functional. Okay, so you notice what we've done, this h has disappeared from everything. It's just analytic continuation of things. So going from the non-compact to the compact, you go between the things like that. However here, which is somewhat, I think, unusual or surprising, is that actually also the optimization problem goes through with this analytic continuation. And again, we get a Riccati equation, which is just slightly different from what we had. And here is, again, the solution, just analogous to what we had for the case of the hyperbolic space, only it's the compact version of such a thing. And here's what you do. It's very straightforward. I guess I'm running out of time, I see. So again, you can do this thing. You get this thing where it's kind of a completion of squares, but not in the linear case. And there are various other generalizations that one can have. And I like to note some of my colleagues, my colleague and spouse of 30 years, Bojana, Bogdan Maslovsky, Lukas Stettner, Peter Mondel, who unfortunately passed away a couple of years ago, Han-Fu Chen, Beijing, Lei Guo, Jacek Jakubowski, Praveen Varaya, and Xing Zhang. So thank you.
So we have time for a couple of questions, if there are any. So that does not seem to be the case. I would like to remind you that at 6:15 here we have the block community lecture. So it's going to be a very interesting lecture. So please do come, and let's thank Tyrone again.